Hi everybody, welcome back to the Feynman technique. This is part two in a series where I try to solve this integral, the integral from 0 to infinity of cosine x over pi squared minus 4x squared dx using Feynman integration. We're not actually going to be getting to this part of it today. We're just going to be, like I said, this is part two of three. On the third part, I'll actually solve that integral I just had up there. Today, our goal is to show this, that the integral from 0 to infinity of 1 over pi squared minus 4x squared dx is kind of equal to negative 1/4 I. And I say kind of because that integral technically does not converge. So don't put this as any sort of like answer on a test, because you won't get points for it. But for the purposes of solving the integral that I'll solve in part three, we can sort of assign the value negative 1/4 I to this integral. And I'm going to show how to get that result right now. You'll see that I already have this stuff set up. This is going to be for our substitution. The substitution we make is that tangent theta is equal to 2ix over pi. And I set up a right triangle based on that. And you can see this is a valid right triangle. And all the other stuff follows from this. Well, except for this part. Tangent theta equals 2ix over pi implies that theta is equal to the arctangent of 2ix over pi. That's just how tangent and arctangent work. And then we have our dx right here. That just comes from taking the derivative on both sides of this. And we have a cosine squared theta being equal to pi squared over pi squared minus 4x squared. You can see that's just true based on that triangle. So let's go ahead and rewrite our... Oh, well, actually, I forgot two important things. We're going to need to change the bounds. So as x goes to 0, we have theta being, well, 0 times x is what? What's 0 times x? It's 0. I'm sorry, what's 0 times 2I pi? It's 0. Arctangent 0 is 0. So theta goes to 0. But what about x going to infinity? And I should not put an equal sign. I should say like going to infinity. What happens there? Well, this x goes to infinity. We could call that arctangent infinity and just call it pi over 2, say that theta goes to pi over 2, but it's not really going to infinity, is it? It's going to infinity, but along the positive imaginary line, not the positive real line. So what value do we assign to theta as 2ix over pi when x goes to infinity? I don't know. And that's where we're going to use this identity that I derived in part 1. The arctangent of x is equal to I over 2 times the natural log of x plus I over x minus I plus pi over 2. That pi over 2 is important, and it's very often left out of this equality right here. And I don't know why, because if it's left out, this is not true. That pi over 2 needs to be there. And I showed that in the last video. I will link in the description. But let's find out what happens as x goes to infinity of arctangent of 2ix over pi. So we're just going to plug in 2ix over pi into our derived expression for arctangent x. So we're going to take the limit as x goes to infinity of, let's see, we'll have I over 2 times the natural log of, now our x in this case is 2ix over pi. So we have 2ix over pi, and then plus I, and then that's over, I'll make that a little bigger, 2ix over pi minus I. And of course, plus pi over 2. Well, pretty easy to see that we can multiply, inside this natural log, we can multiply the top and the bottom, the numerator and denominator, by pi to just eliminate these pi's right here. And then you see we can divide the top and bottom by I because we have a common factor of I in there. All right. So this just becomes a 1. That becomes a 1. This is a 2x. And that's a 2x. Now it becomes pretty obvious what happens as x goes to infinity. This will go to 1. We don't even need these plus 1 terms because as x goes to infinity, this plus 1 becomes insignificant. This negative 1 also insignificant. And then we're just left with 2x over 2x, which is simply 1. And we all know that the natural log of 1 is 0. So this whole thing just equals what we have left over here, which is just pi over 2. So it turns out that, yeah, this implies that theta would go to pi over 2. So it's kind of what we thought. Apparently it doesn't matter that x is going to infinity, or that this value is going to infinity along the positive imaginary line. But we didn't know that to start. We didn't know that that's what was going to happen. So we had to show that using this. We couldn't just plug it into arctangent as is. We had to use this. All right. So, what are we actually doing? We're trying to show this. So let's use our substitution on that. So we'll call our goal integral g, and that's equal to, let's see, our change of bounds says that as x goes to 0, theta goes to 0. And it says that as x approaches infinity, our theta would approach pi over 2. And then our integral is this. We have 1 over pi squared minus 4x squared dx. So let's replace these things part by part. The first thing I'm going to do is multiply this by pi squared and then divide it out. Okay. Now let's replace this with what we know it is. It's cosine squared theta. And then what is our dx? It is pi over 2i secant squared theta d theta. But I'll write that as, let's see, hold on. I want this as 1 over pi squared. And now we're going back to our dx. So our dx is pi over 2i. So I'll just get rid of one of these pi's in the denominator. And then we'll say times 2i. And then we have secant squared theta d theta. That will just cancel that cosine squared theta, and we're just left with d theta. So that equals 1 over 2 pi I times the evaluation of this thing, which is just pi over 2. And that equals 1 over 4i, which is simply equal to negative 1/4 I. And that's it. So, in the first video we derived this, and in this video we used this to derive this, and in our third and final video we will use this to find the answer to this. 4x squared dx. So, yeah, in the third video, we're going to use Feynman integration to solve this using this. This result right here. This result right here. We'll use this to apply Feynman integration to this integral and get kind of a surprising result. All right, well, I hope you enjoyed that. We'll see you next time.